All right, so yeah, this week, the rainbows again. This week we'll cover, I guess, just some fun things or just things I thought were interesting and kind of neat. So today I've got a couple of just, we'll look at optim, the optim function, and we'll look at kernel density estimation, KDE. Wednesday, I thought I would just show you like R-Shiny. I don't know if you had any interest in R-Shiny or even know what that is. It's kind of a neat little thing. And we'll do that. Again, yeah, Wednesday will be our last lecture. We won't have class on Friday. I'll be on campus if you have any questions, and I'll have office hours on Friday, like a long time, 9 through noon or something. You got any questions? And yeah, we'll take it easy, and you have finals next week. And so this class is scheduled at Thursday at 8 a.m. So that's just how it goes. We're at the mercy of the scheduling office. And so that's what we'll do. Okay, well, we'll take a look. All right, so we'll revisit this topic of optimization. And there is this general purpose optimization function called optim, and what we use it to find the minimum of a function. And if you want to use it to find the maximum of a function, you just multiply your function by -1, and then you find the minimum of that function, and that will be the same as finding the maximum of the other function. It takes in, basically you got to provide it 2 arguments. You got to provide it a initial vector par, the parameter estimates, and then the function, fn is the function that you wish to optimize. You provide that. Everything else has kind of some default values. The default method for optimizing is the Nelder-Mead method, which we saw earlier, where you have like the triangle that's like expanding and reflecting and expanding and things like the extending and all sorts of stuff. These other ones we have not really covered. BFGS is like 4 people's names for this kind of gradient descent, and I don't remember what all of this other stuff is. There's like a modified version of BFGS and all sorts of stuff, but we won't worry about that. The Hessian, that's your matrix, second derivative matrix. Okay, so anyway, yeah, the par is the vector of initial parameter values that we want to optimize, and fn is the function that we want to minimize, and the function's first argument needs to be par, or the parameters over which the minimization takes place. And this function, okay, so the requirement is the function has to return a single scalar value. Okay, so you can only minimize a function where the output is producing 1 value, right? Because it's going to just try to do everything it can to get that 1 value to shrink. You can provide some other functions that will return the gradient. We haven't really talked about the gradient, but the gradient is kind of the multivariable version of a derivative. You can kind of think of it that way. And in 102b, I cover gradient descent, which is another optimization method. And what did I write? I wrote Newton-Raphson uses the derivative of the function to find the next value to use, and for multidimensional functions, the gradient is conceptually similar to the derivative. And these gradient-based methods are somewhat similar to Newton-Raphson, okay? And if the gradient function is not provided, optim will use a finite difference approximation, which is similar to kind of our derivative approximation that we did in, I don't know, one of the week 7 lectures, or one of the other lectures. Okay, and you can specify which method to use, and there's other control things. Okay, so let's try an example of a function that we want to optimize. So let's say we want to optimize this 2-dimensional function, x squared minus 2x minus 0.5xy plus 2.5y squared. And so here I'm just going to write a function called g, and it's going to and it takes in x and it takes in y. Okay, and we would just write it this way, right? X squared minus 2 times x minus 0.5 times x times y plus 2.5 times y squared. Okay, and I think we're all very comfortable going from here to here. Okay, but this function will not work with the optim function. The optim function requires that we write a function where it takes in one argument called par. Okay, and par this time is going to be a vector. So in this case, because our function takes in 2 values, par is going to be a vector of length 2. The first value corresponding to whatever we want it to be. So in our case, we're going to say the first value of par is going to be x. The second value of par is going to be y. And then we can say, give me back the value of the function. Okay, but this is how you have to write your functions to work with optim. You have to make it a function of just one vector, rather than provide 2 arguments. So you give it one vector, and then if you have multiple values that, your function is a function of 2 variables, you split that up. You say x is par 1, y is par 2, so on and so forth. If you have, x, y, z, or whatever, you'd have par 1, par 2, par 3, or, however, whatever it is. And this par thing can be as high dimensional as you need it to be. So you can have a function of, say, 27 variables, and that's fine. You just have to find a way to kind of split up par into all 27 individual components. Okay, and so this is how you would do it. This is how you, so here, let me just show you. Let's go to Wolfram Alpha. And let's copy. How do I copy this? Okay. Copy this function. Alpha. For some reason, this. Okay. I hope this works. So this is kind of what it looks like, and it tells us the global minimum is at 40 over 39 and 4 over 39. I think this is a function we used for something else in our class earlier. We used the same function. Okay, so this is the global minimum right here. Okay, and so in R, we have the function g, which is what we've written here, and we call optim, and we give it just some arbitrary initial starting values. I think I'm just going to say -1, 1.5. It doesn't really matter. And then it runs, and it says we found a minimum at 1.0255. The true value is at 40 over 39, which is 1.02564. So we got kind of close, not perfectly there. And then 4 over 39 is 0.10256, and here we have 0.10247. So, not perfect, but moderately okay. And it says, all right, so it ends here, and this is what it considers a successful value here. This is just using the default. You can specify, I want a better, or not better, but so the default is using Nelder-Mead. You can say, I want a different method. And here we can say, use BFGS. So BFGS is kind of this gradient-based optimization, a little bit like, sort of like Newton-Raphson, but not really, okay? And we can see this got it right on the nose here, okay? And it says it found 1.025641 and 0.1025641. And so kind of like Newton-Raphson, it's going to like converge faster, but also it's not guaranteed to converge. I guess very few of these optimization methods are guaranteed to converge. But when it does work, and it works well for these elliptical functions, it works pretty good. And so here we got this, and it says these are the values that will minimize the function. and when x1 is this and x2 is this, or the x value is this and the second value, which is our y value, is this. And it gives you the value at the minimum, which is negative 1.025. Okay? And that's basically it. Okay? And so, you know, it always feels a little bit like I don't know what the right word is. There's a bit of irony in that, like, you know, we spent all of this time covering all of these like optimization methods, but in practice, you'll just use optim on R. And I could have just said, hey, this is how you set up your function, okay? And really, this is like the most important part, is you just, if you got a function, whatever value it is you're returning, this returns a single scalar value. It's just the argument going in has to be, you know, a single vector that you then break up into multiple pieces. Okay, so once you get your function written like this, you can call it, and it will work, right? And that's like the most complicated part of using optim. And I would recommend, if just using optim for if you truly had to optimize a function in R. I think there's merit in learning all of these kind of these optimization algorithms and how these things work, and so, you know, when some of the ideas behind these computational methods, at least some of the theories and ideas behind it. But yeah, in practice, you're just going to end up calling optim, I think, to optimize your functions there. Okay? All right, so here's another example. Totally unnecessary, but let's say you wanted to find least squares regression. Okay, and so here's my data set. X is 1, 2, 3, 4, and Y is 2, 6, 4, 8. And so in least squares regression, we need to fit two parameters, a slope and an intercept, right? And so here I can just call LM. I say fit Y based on X, so LM Y on X, and it comes back and it says, oh, okay, these are the coefficients. Your intercept's going to be 1.0, and your slope's going to be 1.6. And then it's done, okay? Now, we could frame least squares regression as an optimization problem, right? As far as optimization goes, what are we trying to do? We are trying to minimize the total sum of squares, right? The sum of squares residuals. And so, so we can write a function that we want to optimize. We're going to call this sum of squares. And this will, or basically the sum of squares residuals. And so we're going to take in the parameters, a vector. This vector is going to contain the intercept and the slope. So we're going to say par1 is the intercept. Par2 is going to be the slope, b0 and b1. Here's my data. Data is 1, 2, 3, 4. Y is 2, 6, 4, 8. And how do we calculate the sum of squares residuals? Well, we're going to calculate our predicted values as b0 plus b1x. That's going to be our y hat value. So whatever values we currently have for our parameters, we're going to plug that in to get our y hat. We're going to calculate our residuals by doing y minus y hat, the difference between the actual and the predicted values. And then we square all of these residuals. We do residuals squared, and we sum them up. And this is how we would calculate the sum of squared residuals. Okay? And what we're going to say is, R, please optimize this function, find the value of the slope and intercept that will minimize this sum of squares residuals. Okay? And again, it's silly to do this because we have the LM function, but we can kind of just see how does this work with using optim. And so I call optim, and I'm going to just start off at a slope of 0 and an intercept of 0, or I'm sorry, intercept of 0 and a slope of 0. And we say minimize the sum of squared functions, and it says, oh yeah, intercept is 1 and slope is 1.6. These are the values, the two values you're going to use. And so it has succeeded. We got the same match between what LM returns, which is good. Indeed, that is the value of the function that will, the value of the intercept and slope that will minimize the sum of squared residuals. So that's kind of neat, maybe. Okay. Yeah.
So how do we know if we're maximizing or minimizing?
So this always minimizes. This always minimizes. And if you want to maximize, you would just take take the negative of this thing. Okay, you just take the negative. But you know, if you were trying to maximize your sum of squares residuals, what would you end up using? You'd use a slope of infinity and an intercept of infinity, I guess. Okay, and that would maximize. You know, your residuals will be infinity. Okay, or whatever natural limit we can get there. There would probably be no. It would just diverge. Let me give you a first view quiz answer, which is going to be A. A as an apple. A as an apple is your first view quiz answer for today. A. Okay. Do you feel like you could use optim now? Simple enough. Okay. Kernel density estimation. Are you guys familiar with this? Have you seen this before? This word kernel shows up in a lot of places, and it always has a different meaning. It's like, it's just kind of like this stand-in word for so many things. I couldn't even tell you what exactly a kernel is, depending. There's all sorts of stuff. But okay, so we've got kernel density estimation, and this is it's a tool for us to kind of make smooth line approximations for density curves based on a sample of data. And so here's just I'm going to just create a simple sample of random normal data. And this is what a histogram would look like, right? So you take, we have a sample of 60 randomly selected points from the normal distribution. You know, most of them are between 2 and negative 2. You know, as we would expect from a standard normal. But I got a couple not outliers, but a couple values beyond negative 2 out here. And this is kind of our plot, right? And if you looked at this, would you recognize this as coming from a normal distribution? Like, maybe, right? If you do a QQ norm, I think everything would look normal. But this is just coming straight from a random normal distribution. So I think a lot of times we're expecting things to look like this nice, perfectly bell-shaped thing, and it's just you should just make a bunch of random samples of, say, like size 25 that comes directly from the normal distribution, and you'll see you get like wildly different shaped things. And so you might be like, oh, this looks like it's bimodal or something, but yeah, it's just a normal distribution. This is just part of just variance from randomness. Okay, but anyway, you could say, you know what, I want to fit some kind of smooth out density curve, and you'd get some kind of line that looks kind of like this. All right, and this is basically a kernel density estimate. And so the question is how does R draw this line, right? Because it looks like it's doing a decent job of this. And how does R do this? How does R do this? Because all I'm doing, so the command here is the histogram gives me the gray boxes. Rug gives me the actual locations of the values in these little stripes here, like a tiny little carpet or rug here. And then here I'm asking, give me a density estimate of the sample. And it does this, and I say add a line here. And so that's the kernel density estimate. That's what R is doing. And you can kind of mess around with this. You can change the bandwidth. So the default, it has some value here to figure out how it does. And you can say, you know what, I want you to make it smoother. I want you to make it smoother. And you change the bandwidth of the density, and you get a smoother line. And you can do the opposite, and you can say, every dot should get its own little thing. And you get like this really wiggly line. Also, if you look at the rug plot, it actually fits the rug plot a little too well, but that's what it does here, right? And we could, the same things you can do to a histogram, right? You could change the bin width on the histogram, and if I changed, the number of breaks on the histogram, or how wide my bins are, I would get like this really jagged looking histogram that would probably match this red line very well, or I can make the bins on my histogram really wide, and I'm going to get something that matches this thing. So it's similar, except histograms, you're always going to have these rectangles. And then with the kernel density estimate, you're going to get some kind of curved out thing, right? Okay, so here's exactly what I'm saying. So if I change the bin width on this, I get something that looks, like they match up. Okay. All right, so how does this thing work? Okay. Basically, you can think of a histogram. What is a histogram doing? A histogram is basically taking rectangles and stacking them on top of each other, right? So here's like kind of your base rectangle, and it says, oh, there's a point here, I'm going to put a rectangle right here. And then here there's what, 3 points here, so I'm going to stack 3 rectangles at this location. Here there's only 1 value, so I'm stacking 1 rectangle here. Here there's 3 values, I'm stacking values up, okay? So that's what we're doing. With a kernel density estimate, instead of stacking rectangles, it's going to stack little curves, okay? So it's going to drop, by default, the default thing that it drops is like a little normal distribution centered right at each value, okay? So if I said make a kernel density estimate and my data consists of 3 values, -1, 0, and 2, okay, I have 3 total values here. And so you can imagine what a histogram would look like. You would just have like a rectangle at -1, a rectangle at 0, no rectangle at 1, and a rectangle at 2 or something. Or if you changed your bin width, you would have a rectangle of height 2 and a rectangle of 1 over next to it or something, right? So you can imagine what a histogram would look like. And here we're doing something similar, except instead of stacking rectangles or blocks, we're adding like this normal distribution shape thing, okay? But these normal distributions are like, I don't know, they're like things of sand that can stack on top of each other, if this makes any sense, okay? They can add on top of each other. So here is my bin width is 0.1, so each normal distribution curve looks like this. If I change my bin width to 0.25, the normal curves get wider, all right? And these two would kind of add up, and they kind of form this, right? This one still is over here, and it looks like this. Does that kind of make sense? So I'm adding like this slightly wider normal distribution. I'm dropping it down, and then another one drops down over here, and the overlap kind of forms this. And if I make the bin widths even wider, then they kind of combine even more, and so we get this. So again, there's only 3 data points. 3 data points here. And so at this point, because my bin width is kind of wide, now it's getting this smoothed out business over here that's, showing off way over here. And we get that. And as I continue to make my bin width even wider, the 2 that are at -1 and 0 kind of form one super peak that's this tall. And then this one centered at 2 forms a peak right here. And then, now it's spreading out quite wide. Okay. So that's basically how it's going, all right? And so what's happening here is you can kind of see we're adding this tiny little normal curve here, tiny little normal curve here, tiny little normal curve here. I'm adding like 3 normal curves on top of each other, and 1 normal curve, and so we get this shape over here and back here. Basically, I can change how wide each of these normal curves go. And when they add up, they add up to generally to a nice smooth kind of shape here. All right, so that's basically what kernel density estimation is doing. You can actually change the shape that gets added. So the default kernel, or the default little shape that's going to drop down and add up for each of these things, is a kind of this normal Gaussian curve. But if you wanted to, you can change the arguments, and you can have an Epinechnikov kernel, an upside down parabola, okay? But, when you're the person who came up with this, you want your name on the thing, and you don't want to call it upside down parabola kernel. You want to make sure people know it was me. It was me, Mr. Epinechnikov. Okay, or all right. before let me give you your second view quiz answer, which is E. E as in Epinechnikov. Okay. All right. You can also just do rectangular curves. Okay, rectangular. Because of the default plot settings, when it adds these up, they're going to look like trapezoids because the way it draws the lines is it like calculates the value here, 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 and then it just connects them. And because it's like the resolution is like a little bit wide, it's the next value. Yeah, it goes up, but it's going to look a little bit like a trapezoid. You can also add triangles. You can add kind of like when you plot a cosine, like a negative cosine, it's going to like a sine wave, and you just kind of take it from 0 to pi. Or no, 0 to 2 pi for cosine. Okay. So, here is the upside down parabolas, the Epinechnikovs, and you add this, and so you get these funny looking shapes, especially when it's like what happens when the two overlap, you get like this little, I don't know, funny looking shaped things. Okay. Okay. So this is you add two parabolas, and this is like you get these like little gnomes. Maybe they're like yeah, I guess. And here we go. So they add up, and they kind of form these little bumps. All right, here we are with the rectangles. Okay. And so when they stack up, so here they are, they're almost gonna touch, and when they stack up, you get this kind of funny business, right? It's like a little pyramid, and as they get wider, you get even just weirder stuff. So this is the overlap of, I guess, 0 and 2 overlap here, and 0 and -1 overlap here, but there happens to be like a little gap between here and here where there is an overlap between 1 and 2. Okay. With the triangles. So the triangles, when they overlap, you end up getting a flat thing, which kind of makes sense, right? Like this side's going down at the same rate, this side's going up, so you get this flat kind of I don't know. Because they add up and fill in with each other. And so this is something. So one thing to note is a lot of times we look at like a kernel density. So I'm going to scroll all the way back here, right? You look at a kernel density estimate, and you feel like, oh, do we have a formula for this curve? And we don't. There's no formula form for this, right? A lot of times we think there's, we see a smooth line on a graph, and we think there's a formula, but it's not. All the computer is doing is just saying like, okay, at this location, what is the sum of all of these different parts of these different curves? If I add them together, it's going to be right here. And then it just moves it's moving at kind of a resolution of, say, like, every 100th value. So at -3, what values add up here? And at -2.99, it just looks at all of the different things that would add up, and it adds them up. At -2.98, what are the things? And so when you do the kernel density estimate, you just get a sequence of values going from, say, -3 to 2, at intervals of 0.01. And so you get a bunch of values that we can kind of connect and draw this smooth curve. But you ask, hey, what's the formula that defines this thing? There's no formula for it. It's just, we're just adding a bunch of these things together. Okay, so the computer's not going to give us some kind of closed form solution for this. And so it's just adding. It just says, hey, at this location, what are the values of the different curves that add up? And it just says, oh, these are the things that add up right there. Okay, this is a cosine, and so this is it's supposed to look like a kind of a cosine thing, and they kind of add up. That looks a lot like the normal Gaussian one, but I guess it's a little bit different there. Oh, I guess I went through all of these slides really quick. Okay, and so that's that. That's kernel density estimation. which I think is just a handy little tool to kind of enhance your graphs. ggplot has I think a geom underscore density that you can add to kind of add these kernel density estimates, and they're all kind of calculated in similar ways, and you can always kind of specify. Usually the default is the Gaussian one. As far as what bandwidth should you use, okay, the default settings of density will calculate the bandwidth using some kind of formula, all right? Either it takes the standard deviation or the IQR divided by 1.34, and it uses that, whichever one is smaller. And then it takes, and then it just does this formula, 0.9 times the spread, and then it takes the number of points that you have raised to the negative 0.2 power. I have no idea how they decided this was a good number, but this is the formula that they use. Now you can, like you've seen here, I've been manually selecting these bandwidths just kind of for illustrative purposes, and you can decide how, again, just like when you make a histogram, how do you decide how many bins to create, right? It's kind of an arbitrary decision, and you just kind of do one and you say, well, this looks good, or this looks good, or this, you know, there's a little bit of an aesthetic choice. And I think it's similar for kernel density estimates. Is you can say, oh, well, this looks pretty good, or, you know, I'd rather have this or something, and so you have all of that. All right. Oh, yeah. So one thing is that the kernel density estimate, because it's just adding these things, it's going to often produce tails in regions where no data exists, right? And so if you were to take, say, some exponential data, right? So data from an exponential distribution where you know the exponential distribution can only produce values that are positive, okay? Because it's going to just take some kind of curve and add it to whatever value you have. Let's say the lowest value you can produce is, say, you know, -1, or there's a hard cutoff somewhere. It's going to often produce something that looks like there's a tail on, you know, in a region where you know it's not possible, right? If you take some uniform data from 0 to 1 and you say, hey, give me a kernel density estimate, it's going to spill off into areas like negative values and areas past 1, because it's just adding these, you know, Gaussian things that kind of spread wider than where the values are actually located. And so I think some of the, I think ggplot corrects for this and won't draw density curves beyond the minimum and maximum values in your data set. But the default density estimate is not going to do that. And so you're going to get kind of values way out here and way down here, even though there's nothing there that exists, even though this is based off of just 3 values, -1, 0, and 2, to kind of draw this. All right, well, this is all I have planned for today. Let me give you your last view quiz answer, which is the letter B. B as in bear, B. And we will end here, and Wednesday will be our last class. I'll go over what you can expect to see on the final exam, and maybe I'll cover a little bit of stuff from R Shiny, just a kind of fun little demo there, and then and that will be that. Okay, we'll see you guys on Wednesday.